Welcome to everyone. Previous class we have discussed about of different types of molecules, that is linear molecules, and we have discussed that is symmetric top molecules. Symmetric top molecules that have two types. One is prolate, another is oblate. This prolate type of molecules are mainly C and B type point groups, and these are D and H point groups. And we have discussed CNB like molecules like NH3, and this principal axis Cn where n is greater or equal to 3. This condition should satisfied. And next type is linear molecules. Point groups, we know that D infinity H, C infinity B, all types of molecules fall in the linear molecules. Symmetric top molecules, and R1 is spherical top molecules. Spherical top molecules. Here all the molecules like TD highly symmetric point groups, octahedral like type point groups will fall in spherical top molecules. Examples like CH4, SF6. And if I talk about a 4, that is asymmetric top molecules. This all the C2B point groups or CS type point groups like water, and all CS point groups where only element E is present. So these are the 4 types of molecules we have, and they divided that now which molecules, what type of point groups we can get. So we have already discussed this. So today class we focus on that. We have also discussed that the center of gravity. We have discussed on that center of gravity. Center of gravity. What it means is that, let's say that one molecule is rotating along this, means this molecule is rotating along this point. So whenever this molecules will rotate like this, so this is the center of gravity for this molecules. So the distance between these molecules which is rotating from this center, that is r, and let's say this has the mass m1. So similarly, if we say that molecules is two molecules are rotating, let's say this molecules and this molecule, same molecules, let's say m1 and m1, same mass. The center of gravity will lie somewhere in the middle. Okay, this is the center of gravity for this molecules. So what we say that center of gravity, what it says that, let's say this mass is, let's say mass is m1, and distance between this is the center of gravity, and here this is the center of gravity. This is the center of gravity, means to this point these molecules are rotating. Okay, so this is center of gravity. So center of gravity, what it says that here, suppose this is r1, and let's say this is r2, and this is, let's say, m2, and then center of gravity, the condition is m1 into the distance from center of gravity r1 into this molecules m2, and the center of gravity distance r2. This always satisfy for center of gravity. Okay, and since now this m1 equal to r1, because m1 equal to m2. So here that this point, then r1 equal to r2. Okay, so since these are mass equal, so center of gravity is like this, like middle of the middle point of the two molecules or particles. Now let's say if that one molecule is this and another molecules, let's say this. So center of gravity condition is always same. Center of gravity, what it says that, suppose this is m1 and this is, let's say, m2, and the distance, so center of gravity is m1 and the distance m1, and whatever the distance, suppose for this center of gravity r1 has to be m2 into r2. This is the conditions for center of gravity. It means I say that since m2 is greater than m1, because this is the heavier atoms, so if this is greater and we have to satisfy these conditions for a center of gravity, then what, that r2 should be less than r1, because this m2 r2, if this is high then this has to be low to satisfy or to equal with m1 r1. So r2 will be like somewhere near to this, it means this r1 has to be low, because m2 is greater than r1 should be low, so that satisfy this condition. So r1 will be like somewhere here, sorry, r2, and r1 will be this one. So for heavier atoms, center of gravity lies towards the heavier atoms. This is the center of gravity. Why it should lie? Because you have to satisfy these conditions. This is the conditions of center of gravity. Okay. So we will discuss that moment of inertia for linear molecules, linear homogeneous molecule, and linear heterogeneous molecules. So we have discussed in previous class that what is moment of inertia, and let me give the quick introductions that we are discussing about of the like linear momentum. What is linear momentum? That is, we can say mass into any velocity. So this I can write mass into velocity or any speed. Okay? Mass into velocity for linear momentum. Similarly, that angular momentum, this is also has to be since this is also momentum, this is also momentum, this also has to be some mass, but since this angular momentum, we have to rotate the molecules, so here that moment of, instead of mass, moment of inertia will come, moment of inertia into here velocity, here angular velocity. Let's say this is angular velocity. So angular momentum is this and linear momentum is this. It means that this is velocity and this is angular velocity. So from here, if you observe this linear momentum, angular momentum, so this moment of inertia somehow says about of the mass, because this also mass into velocity, this also the same momentum, so this also has to be some relations with mass. So why we are interested about of I, because in moment of inertia we will study for our energy. Whenever we are studying about of our energy levels, on that time we use that moment of inertia. That's why this moment of inertia we are interested. And this moment of inertia definition also we see that the amount of force required I is, let's say this is moment of inertia, moment of inertia This is represented by I. This is the amount of force. So amount of torque, actually you can say amount of torque. Torque means that amount of force required to rotate a molecules. So I can say the amount of torque required to rotate the molecule. That is known as moment of inertia. So this moment of inertia, what its formula mathematically? How can you say mathematically? I is equal to mass into this is reduced mass into r naught square. Mathematically, moment of inertia is I. Let's say moment of inertia denoted by I equal to u naught. This is the reduced mass upon r square. This is the reduced mass. Okay, and this is that distance between moving particles and center of gravity. That we have discussed in the previous class. So now we are discussing about of that linear. We will discuss about of the moment of inertia for moment of inertia for linear molecules. Let's say that molecules is same atoms. Let's say one atoms here, another atoms is here. Let's say about of O2 type molecules. So since this is also M1, and let's say I'm talking about M2, and or I will give the same name. Let's say this is M1 and let's say this is M2, and since so center of gravity formula is, so condition is center of gravity condition is M1 R1 has to be M2 R2. So because here that M1 equal to M2, because both oxygens I am taking, so R1 has to be R2. So the center of gravity will lie somewhere in the center, in the middle of the two oxygens. So what is say about of the moment of inertia? Then moment of inertia is this is the any reduced mass. So here I will take directly this. Let's say I will add it M1 and R1 square. This is the moment of inertia. So if that linear atoms, then directly we will take about of the, if the same atoms, then directly we can take M1. No need to take reduced mass. So why we need to take reduced mass? We will discuss. So this is M1 R1 and this is M2 R2 square. And since M1 R1, or we can say M1 equal to R1 and R1, so M1 equal to M2, R1 equal to R2, I can write this to M1 R1 square, because these both are equal, so I will take like this. So this is the reduced mass. So this is the moment of inertia if linear molecules with same ends, means with same atoms, like O2, or you can take H2 or Cl2, like that molecules, the moment of inertia will be I equal to M1 R1 square. because both are equal here. Okay, so now if we talk another conditions, the linear molecule with different ends, like you can take a lot of HCl type molecules, HBr, this type of molecules, means having the two different ends. Let's say here is one molecule and another molecule is this, means heavier than this atom. Let's say this is Cl and let's say this is H. So this Cl is heavier atom than H. So what the center of gravity, the conditions is center of gravity what it says that, let's say this is M1 and let's say this is M2, and the center of gravity condition is M1. If you have the distance R1, that has to be M2 and R2. Now because here M2 is greater than M1, so to satisfy these conditions R2 has to be less than R1. It means that R2 will be lie somewhere here, that R2 should be less than R1. If this is the R1, then this R2 should be smaller, means the center of gravity somehow lies towards the heavier atoms. So this center of gravity lies towards heavier atoms. Okay, so now so how can I write here? So moment of inertia, that is M1 R1 square plus M2 R2 square. So for this, since the different, because M1 not equal to M2 and R1 not equal to R2, here we use the reduced mass. We know that reduced mass, that is this is equal to, so this we know why we use reduced mass, that we can and this is the basic things that we may know it, that 1 upon this reduced mass equal to M1 plus M2, and if I will add it, then what you will get? M1 M2 plus M1. This is 1 upon reduced mass. So reduced mass is equal to M1 M2 is M1 plus M2. This is the reduced mass. So if I put this value here, and also that this R1 and R2 are different, so this the total reduces, let's say the R0. This R0 equal to R1 plus R2, so I can use this R. So total, if I talk about of that moment of inertia, then this will be U0 R0 square, where U0 is this and R0 is R1 plus R2, and right, where R0 equal to R1 plus R2. Okay, so these are the moment of inertia we can calculate if the linear molecules with different ends. Okay, now we will discuss for that how to calculate the energies for a rotating molecules. So what we discuss further, let's say this is O2 molecules. So if it is like this, like say this oxygen molecule is rotating here and this. Means we are discussing about a rotational spectroscopy where molecules will rotate, and we will also discuss that how that molecules which molecules are rotational actives, that is vibrationally which sorry, microwave active. For rotational spectroscopy we are using microwave. So what type of molecules microwave actives we already discussed, that should have permanent dipole moments, or that uh, change in dipole moments, that dipole moments should be changed. So what we already discussed, that is if the molecules is rotating like this, so due to this molecule rotations, what happened that the due to rotations of molecule dipole moment will change. That we already discussed, that because of the directions is changing, and since dipole moment is a vector quantity, so if either magnitude or directions, if any one will change, then the dipole moments will change. So we already discussed that things, that dipole moment is a vector quantity. It is a vector quantity, and we know that vector quantity means both directions and magnitude. If any both we have to consider, and if any one is changed, then the dipole moment will change, because this is a vector quantity. And we know that, like if you discuss about HCl molecules, then here if say delta minus is delta plus, then dipole moment is this directions. So here the dipole moments formula is, that is q charge into r, that is the distance between the two atoms. So q into r. Now here that the distance, or uh, the length between the H and Cl is fixed, and q charge is also fixed. So here, according to dipole moments, if dipole moment is not a vector quantity, then the dipole moment is not changing, means this is microwave inactive. But since this is a dipole moment, so whenever you are rotating these molecules to this directions, then what happened here, the direction is this directions, and whenever you are rotate, then Cl goes to like this and H goes to like this. So now the directions is become like this, so directions is changing. So since direction is changing, so since the dipole is a vector, dipole moment is a vector quantity, so if any one will change, means the dipole moment will change. So due to the change in the directions, the dipole moment will change here, not due to the magnitude. The magnitude both q and r is same, only direction is changing. So if any one will change in a vector quantity, then ultimately that vector will change, means the dipole moment is changing. So here, due to change in the directions of the molecules, the dipole moment is changing, not due to the magnitude. Okay, so whenever this molecules is rotating, like here is here, after rotate, let's say, so this molecules is become like this. So again it will rotate. So the dipole moments, just a minute. So dipole moments is, so here the direction like this, the mobile molecule is rotating, so dipole moment is changing. So that due to this dipole moment change, so the frequency also change, means I write here, so due to change in dipole moments, or I can say whenever this molecule is rotating, so it is rotating with some frequency or with some energy. and energy, we know energy is h nu, means it is rotating with some frequency. Because it is rotating means whenever molecule is rotating, it means it is rotating with some energy, and it is energy have the frequency, energy is h nu. So here some frequency, with some frequency the molecule is rotating, and what happens, let's say these molecules, this molecule is rotating with this molecule is rotating whenever we give some angular velocity, whenever we give some angular momentum, means some energy you have given. Energy means h nu, this is the frequency, and this is the Planck's constant. So if it is rotating with some energy, it means it is rotating with some frequency, and whenever we give to this rotating molecules any electromagnetic radiations to it, then what happened, that in electromagnetic radiations, it has magnetic field and electric field it have in electromagnetic radiations. It means that it has some frequency. So whenever if we are giving the some electromagnetic radiations, means we are giving that microwave. So a microwave means that magnetic field and electric field is there. So whenever we are giving it to the molecules, the molecule is already rotating with some frequency, and we are giving these radiations. This radiations has its own frequency. So whenever you give these electromagnetic radiations to these molecules, and if the frequency of this molecule, means electromagnetic radiation means it has its own frequency, whenever its frequency and this frequency, this molecule is rotating with some frequency, so this frequency and this frequency if matches, if frequency of rotating molecules, that is due to change in dipole moments, if frequency of rotating molecules and frequency of electromagnetic radiations which is given to it matches, then what will happen, that if that this molecule is rotating with some frequency, and we are giving the electromagnetic radiations to these rotating molecules, if the frequency of these molecules and the frequency of electromagnetic radiations if matches, then these molecules observe that frequency, this molecule observed or gain the observed that frequency, and frequency means that energy h nu. So if the frequency increases, ultimately energy increases. So if the molecules observe that frequency, then after observing that frequency, the molecule, I can write, and the molecules shift to high energy. So whenever these molecules observe the frequency of this electromagnetic radiations, if it matches, then it observe, it means its frequency increases, means its energy increases, then this molecules increases its energy, it means that molecule rotate more speedily, means now it is rotating slowly. After getting this frequency, the molecule rotate comparatively to this, higher rate it will rotate. Okay, so this like whenever it gaining the molecules, so whenever it gaining the frequency and it shifting to high energy, so here we say that which frequency, it means some selective frequency only it can uh, gain. It means that which frequency it match with its frequency, then only it gain that frequency, otherwise it not gain frequency. It means that it says that the observe of the frequency is quantized, means that amount of frequency with it rotating that matches, only then it observe, otherwise it will not observe. So that is explained by it means what I say, that whenever it observe that frequency, after observing frequency it shift to the high energy, so it observe that frequency, and if that frequency will match with this frequency, then only it observes and it shift to higher energy, otherwise it will not observe. So let's say here at this energy, our O2 is rotating. Okay, at this energy O2 is rotating, and we are giving the electromagnetic radiations to this electromagnetic radiations. So whenever you give electromagnetic radiations to this, here that O2 is there, that is rotating. So whenever you give the electromagnetic radiations, and if the electromagnetic radiation, it has its own frequency, and if its frequency and this rotating molecule's frequency if matches, then it observes that frequency, and let's say this is the low energy, let's say this is the low energy and this is high energy, let's say this is higher energy, then it observes that frequency, and it will frequency increases means energy increases, so it will go to the high energy, and now this O2 come here and rotate here, means more fastly, means more rotating means it will come to the high energy. So what it says, that it observes that frequency only if it matches, means let's say here also, so if it like say it has that 10 frequency it is giving, and it has it own has, let's say 10 frequency, and it has 10 frequency, and this frequency is, this energy is with 20 and this is with 30. So this energy is 30 energy, means let's say this 20 joule, and this, let's say this is 30 joule. So whenever it gives this frequency, it gives frequency, then it observe the frequency, and it will gain the 10, let's say this is 10 joule, so it gives the 10 joule frequency, then it observes this 10 joule and shift to the 20 joule energy, it come to here. But whenever this frequency is, let's say 5 joule, and it not observes this 5 joule, because it observes the 5 joules, then it come to somewhere here 15 joule, but here there is no energy level. Okay, that what it means, that it observes that frequency which matches the its frequency to reach the higher energy, otherwise the other frequency it will not observe, like say 5 joule, 22 joule, or if say 12 joule, if it gives, it will not observe that frequency, because it observe also, then it will no energy levels, like 12 joule no energy level is there, so it will observe either 10 joules only, or it may observe 20 joules to shift the 30 joules, that we will discuss it will go or not. So here if it observes 20 joules also, there is a energy level is there, and it observes 10 joule, then energy level is there. So if the molecules now is here, let's say the molecules is here, and if you are giving that 10 joule, then it observes here, and it can go to this energy levels. or another let's say 40 joule, another let's say 50 joule, so like that. So that energy level is quantized. It means that it absorbs only that particular amount of energy or frequency, which by gaining of which it will shift to the energy level which is quantized. It means that it absorbs only a particular amount of frequency only which matches its frequency. Okay, so now this energy levels, it is quantized. So this how I am taking this is just for arbitrary values. These are the not actual. I am taking just for example. Actually, how these energy levels are quantized, that is given by the Schrodinger equations. That is given by Schrodinger equations, that how the energy levels are quantized and how energy levels like with how which amounts, like I write here 20 here 30 joules, that actually not that actually energy level is given by Schrodinger equations, and this equations is the derivations I am not doing. The derivations we can study in quantum chemistry, so directly I am writing the formula, so that is important for these chapters. That equations is energy equal to 8 pi square I j plus 1. So this is the equations given by the Schrodinger. This equation is derived from the Schrodinger equations. So with these equations we can derive these energy levels. Okay, so we will derive it. Let's say this h is Planck constant, and this I is moment of inertia. So that's why we are studying the moment of inertia. I discussed about of that why moment of inertia is important, because we use that moment of inertia here whenever we are doing the energy levels. And this J is rotational quantum number. Rotational quantum number. So how these equations give that? Let's say so that I'm writing here E equal to h square 8 pi square I. This is in joule. But another things before we write or know how this energy levels is given by these equations, so we should know one more things, that this is in joule and we are studying in the spectroscopy. So in spectroscopy the spectroscopy data are given in centimeter inverse. So whenever you see the spectroscopic data, that experiment values, that is given in mainly in centimeter inverse, but this equation is in joule, so we have to convert this joule into centimeter inverse to understand that data. So we mainly in spectroscopy we will talk about a centimeter inverse only. So you will talk this joule in centimeter inverse. So how will you convert this joule to centimeter inverse? So we know that E equal to h nu, and also we know that this nu equal to c lambda, because c equal to nu lambda. So I will put that this nu here, that is h c upon lambda. So now what I will do, that this is the wave number, this is the 1 by lambda. So we know that wave number is 1 by lambda, and this wave number is explained in centimeter inverse. So if I talk about of this 1 lambda, and if I divide it here, E upon Hc, then this is become centimeter inverse, because this is wave number and this is, so since this is centimeter inverse, then this has to be in centimeter inverse because these are equal. So what you do that here, E, if you divide by Hc, then that become centimeter inverse. So what you will do, because E Hc is equal to wave number and that is centimeter inverse unit, and we know that E is, here we derive h square 8 pi square I j plus 1. Okay, so now for getting centimeter inverse, this is in joule. So if I divide by E upon Hc, that is equal centimeter inverse. Here E is this value, so I will put, because if I E divided by Hc means here also I have to divide Hc, pi square I divide by Hc. This is in centimeter inverse, because this is centimeter inverse, thus this has to be in centimeter inverse. So if we cut it, let's say E upon Hc, I can say E dash, then this I can cut here, so that will become h 8 pi square Ic j plus 1. This is the centimeter inverse. Okay. So this is the energy, this is the equations or the energy we will use to derive this energy levels. Okay, now if you notice here in these equations, what you notice that h is Planck constant, so this is a constant, and 8 pi square is constant, 8 pi square, and c, this is also constant because c is the speed of light, this is a constant, and I is moment of inertia, that is u naught, that is reduced mass into r naught square. So if we are talking, if we talk one particular molecule for an experiment, means if we fix the molecules, it means if we fix the molecules, let's say if I talk about any O, then here that this distance is fixed, distance fixed means r is fixed, and this mass is also, I am talking for this experiment, I am talking only for O2, then the mass is also fixed, mass fixed, and this u naught is, we know that is equal to m1, this is m1 m2 m1 plus m2. So if the masses is fixed, then this is also fixed, and r naught equal to r1 plus r2. So distance is also fixed, then this is also fixed, means I is fixed. It means that whole the value is getting fixed for one particular atom. So for one, so I can say or you can say if we fix the molecule, then this is fixed, so I can write the molecules, then this h 8 pi square Ic, this is fixed, so this become a constant for a one particular atom. So I can write here, so this whole is a constant, so I can write this as any constant, let's say b. Okay, so these equations have changed to E dash. So if I fixed all these things, then this become b, and this j plus 1. So these equations we get for one molecule, or you can say for fixing one molecule. If the molecule will change, then this b will change, because b has I, this I will change. Okay, so if we fix molecule, okay. So if I fix the molecules, so generally in experiments, whenever we are doing that, we fix one molecules. We first we observe, we talk about of all the energy levels for that molecules. Next only we will shift for another molecule. So for that particular molecules, this B is fixed for whole the experiment. So the energy levels are fixed. So whenever I am talking about of this energy levels here, so we derive that equation, that is B j plus 1. Let's say for if we are talking about of O2, then this, so for this O2 the energy levels, or if we take out of the for CO, so the energy levels will be like this. And this energy levels, if you observe here, this is energy, or I can write here, this energy test is B j and j plus 1. So if you observe here that this B is constant, so E is only, this is constant, so E depends only J. If J will change only, then E change, because this is already fixed for CO2. Okay, if you talk other atoms, then for that B will change, but if you talk for CO or whole experiment, then B is fixed. So E is depend only, E dash depends only on J value. Okay, because B is constant. So if I write here J equal to 0, if I write J equal to 0, then E will becomes how much? So here I write J equal to 0, then E dash equal to, that is B 0 and 0 plus 1, that is going to become 0. And if J equal to 1, then E dash becomes B 1, and this 1 plus 1 2, that is going to become 2B. And again if I write, if J equal to 2, then E dash becomes, because it only depends on the J, because B is fixed for CO molecules or any molecules, because for whole experiment CO is fixed. Okay, so that is going to become 2 3J, that is going to become B 2 3, that is going to become 6B. So similarly, if J equal to 4, that is going to become, E dash is going to become that is, sorry, here 3, then 3, this is 4, that is going to become 12B. Okay, so here J equal to 0, J equal to 1, J equal to 2, J equal to 3, then this is going to become, so when J equal to 0, E dash is going to become, this is the energy, E dash or energy, then that is going to become how much? 0, and this is going to become how much? 2B, and this is 6B, and this is 12B. Like this it is going to become J equal to 4, then this is going to become 20B. Like this we can calculate by putting the J value, J pi, then this is going to become 30B. Okay, so these energy levels are derived by using this equation. So here I draw the, just for giving examples, this diagrams. So actual diagrams will look like this by using these equations. How these equations has came? By this equation, and this equation is given by Schrodinger equations. Okay, so this is in let's say this is in centimeter inverse. So if any molecules, let's say CO is rotating here, then whenever you give the electromagnetic radiations to here, electromagnetic radiations, then it is rotating with some frequency, and whenever you give electromagnetic radiations, it has its own frequency. So if the frequency of this electromagnetic radiations, and if this frequency, if the art and the if art and the energy it is going to be 2b, then only it will shift to this higher energy, otherwise it will not go. If it is more than, then also it will not go, because no energy levels, and it is less than, then also no energy level is there. So these energy levels are quantized. So if that's why we say that if the frequency of this electromagnetic radiations is matched with the frequency of the rotating molecules, then only these molecules observe this frequency. Frequency means energy, and it shift to the higher energy. And if it is not matching, matching means it has to come to this energy levels, then only it will observe that frequency or energy and shift to this energy, otherwise that will not shift. So these energy levels are quantized, and this energy levels is given by Schrodinger equations, and the equation is these equations. Okay, now we will move to the let's say this is the energy levels, J equal to 0, J equal to 1, J equal to 2, J equal to 3, let's say J equal to 4, and let's say this is the energy, and this is 2b, this is 6b, this is 12b, this is 20b, and J equal to 5, this is 30b. So this energy levels each look like this. So whenever the electromagnetic radiations, whenever you are giving that electromagnetic radiations to this, then if the molecules are there here, CO molecules, let's say I am writing CO molecule at 1 dash 0, then here CO molecules is like this. So this molecule will shift to the higher energy order. But now the question is that how many CO will shift, means what is the population distributions. It means, so whenever I say like this here, that so many let's say CO molecules are there, so many CO molecules are rotating. Means whenever you say that 1 mole of CO molecules rotating, it means that 6.022 into 10 to the power 23 molecules of CO are rotating. So this is very high value, so let me take this value, this is high value, but taking example, let's say I take 1000 molecules. So 1000 molecules are rotating like this. Okay, so let's say 1000 molecules, actually see this 6.022 into 10 to the power 23 molecules are rotating like this. So for simplicity, let me take 1000 molecules. 1000 molecules are rotating. So whenever you give that so today up to this we will discuss for